Hello everyone. We're going to continue the discussion about probability of an event. Let's have the theorems on probability. The probability of the union of two events, event 1 and event 2, or for the two events A and B, the probability of the union of the two events A and B is the sum of the probabilities A plus B plus P of B minus the probability of their intersection. Example. The probability that an American industry will locate in Shanghai, China. So let us have that one as event 1 would be Shanghai. And let's have event 2 to be Beijing. So the probability that American industry will locate in Shanghai, China is 0.7. So the probability for event 1 is 0.7. While the probability for the event 2 for Shanghai, China, for Beijing, China is 0.4. And either Shanghai or Beijing or both, so either, so that would be the probability for event 1 union with event 2 is 0.8. What is the probability that the industry will locate in both cities? Both cities means it would be in Shanghai and at the same time in Beijing. So this is the unknown. So using this formula, that would be the probability of event 1 union with event 2 would be equal to the probability for event 1 plus the probability of event 2 minus the probability of event 1 intersection with event 2. We are given with event 1 intersection event 2 to be 0.8. While for probability of event 1, it is 0.7. The probability of event 2 is 0.4 minus the unknown, the probability of event 1 intersection with event 2. We can transpose this to the other side, so that would become the probability of event 1 intersection with event 2. And then we have 0.7 plus 0.4 is 1.1. And then transposing 0.8. So we have 1.1 minus 0.8 or 0.3. How about neither city? For neither city, so this is for letter A. For letter B, neither city. So that means not either. So E1 union E2 prime, not either. So that would be 1 minus the probability of E1 union E2. So that would be 1 minus 0.8, and that is 0.2. If the two events are mutually exclusive, recall that when we say that the events are mutually exclusive, the probability that the intersection of the two events A and B would be 0. So the third term the minus the probability of A intersection B. Since this is 0, so this can be cancelled out. So for 3 or more events, we use this formula. A union B union C is equal to A plus B plus C minus the intersections taken 2 at a time plus the intersection taken 3 at a time. While if we will be having mutually exclusive events of 3 or more, it would just be the sum of the individual probabilities. Example, if A, B, and C are mutually exclusive events. So when you say mutually exclusive events, there's no intersection. So graphically, we can say that this is A, this is B, and this is C. What is the probability of A? It is 0.2. How about B? 0.3. While for C, 0.4. The total probability of the sample space should be 1. But if we're going to add this, 0.2 plus 0.4 is 0.6. Plus 0.3 is 0.9. So there is 0.1 missing so that we have a total of 1. Determine the following probabilities. A union B union C. Since they are mutually exclusive, this is equal to P of A plus P of B plus P of C. So that would be 0.2 plus 0.3 plus 0.4 equal to 0.9. How about the intersection of the 3? Do the 3 circles intersect, or do the 3 sets intersect? No. So therefore, the intersection of the 3 is an empty set. How about the intersection of A and B? Yes, it is also 0. How about the union of A or B? So the union of A or B is 0.2 plus 0.3, so that's 0.5. But the union of A or B does not have a common region to C. So that means the intersection will be 0. How about A prime intersection B prime intersection C prime? For this one, we can use the De Morgan's theorem. So that this would now be equal to A union B union C prime. We will be inverting the senses. So A prime, B prime, C prime would be A, B, C, and the intersections would now be union, and then we take the complement. Or we take everything except A, everything except B, and everything except C. So the region that is being highlighted here would be this one. So that would be the 0.1, which is the same as the complement of A union B union C. Now, conditional probability happens, or conditional probability is the probability that a certain event would occur given that a previous underlying event has already happened, or you know already the underlying event. So the conditional probability of an event B given an event A is denoted by the probability of B given A. So the probability of B given A is the intersection A intersection B over P of A. For P of A should be greater than 0 because P of A serves as a denominator, so division by 0 is not allowed. So to select randomly implies that each step of the sample, the items that remain in the batch are equally likely to be selected. For example, 6 parts are selected randomly without replacement from a bin of 50 parts. The bin contains 3 defective and 47 non-defective parts. What's the probability that the second part is defective given that the first part is defective? So for this one, we have 50. This is divided into 2 parts, the 47 part and the 3 parts. So this is the non-defective, this is the defective. If we're just going to perform the experiment in this way, so we know that the probability of non-defective is 47 over 50 and the probability of defective is 3 over 50. Now, the problem is if we know that the first is defective, is non-defective, and what if the first selected is defective? If the first item selected is non-defective, so we now have 46 items which are non-defective, and there are still 3 which is defective. So the probability of selecting, what is the probability that the second part is defective, given that the first is defective? So the probability of getting defective given defective. So for the first one, the probability of defective given defective, so if we know already that it is defective, if we know already that the item is defective, so there are 2 remaining defectives left, and then still there are 47. So the probability that the second is defective is 2 out of 49. Similarly, we can get the probability of defective given the first one is non-defective. It is 3 over 49. So the probability changes depending on the underlying event that happened. Let's have an example for conditional probability. Consider the data on wafer contamination and location in the sputtering pool shown in the figure below, 2-2. Assume that one wafer is selected at random from this set. Let A denote the event that the wafer contains 4 or more particles. So 4 or more. So that would be this group. And let B denote that the wafer is from the center. So this is B. Determine the following. P of A. P of A is, so P of A given B, P of B given A intersection B, and A union B. So for the probability of A, that would be 0.11 plus 0.04, or simply it would be 0.05 plus 0.1, which is 0.15. For probability of A given B, So A given B is the intersection of A and B over the denominator P of B. The intersection between A and B, so you can see that they intersect at 0.11. While P of B, this is B, so the total is given as 0.72. So the quotient 0.11 over 0.72 is 11 over 72 or 0.153. For P of B, so we have solved that already. P of B is 0.72. So that is the sum here. P of B given A. So B given A is the intersection of A and B. So it would be intersection, but this time the denominator is A. So the numerator is the intersection, denominator is, it should be P of A. So 0.11 over 0.15. Since P of A is 0.15, A intersection B is 0.11. So that's 0.73. Next is the intersection of A and B. So the probability of the intersection of A and B is 0.04 plus 0.07. That's 0.11. While for A union B, the union is A, B, and the intersection. So we're going to add 0.72 plus 0.01 plus 0.03. So I think that's 0.76. If we will be cross-multiplying the denominator from the conditional probability, the probability of A given B is equal to the probability of A intersection B over P of B. Cross-multiplying this, we will be having A intersection B is equal to A given B times P of B. Same is true for the probability of B given A. Thus, for any three events, we can have this one. So, we can now apply the multiplication rule that P of B is equal to P of B given E1 times P of E1, P of B given E2 times P of E2, and so on and so forth. So this time, let's have the independent events. So if the second event or the second outcome is not affected by the first underlying event, then we say that the events are independent. So the conditional probability of B given A, if the conditional probability of B given A is equal to P of B, then we say that the events are independent. The outcomes of the experiment in event A does not affect the probability that the outcome is in event B. And two events are independent if and any one of the following events or any of the following equivalent statement is true. The probability of A given B is P of A. The probability of B given A is P of B. And thus, for independent events, the probability of A intersection B is equal to P of A times P of B. Equivalently, for complements, the probability of A prime intersection B prime is equal to the product of A prime times the probability of B prime. So for multiple events, it's just the product of their individual probabilities. So let's have this example. A small store installed a diesel power generator for emergency power outage because they function independently of electric power. The past history of the town indicates that on the average, 5% of the days, the town loses electricity. So this is with electricity. This is no electricity. We have electricity 95% of the time. So 0.05, no electricity. That is why they use generator. So the probability that a generator will not function is 0.02. This is the failure rate of the generator. So it would be functioning P of G 0.98. On a given summer day, what's the probability that the store will be totally out of power? When do we have totally out of power? We say that there would be total out of power when there's no electricity and the generator fails. So that would be no electricity, and at the same time the generator fails. So that would be P of E prime times P of G prime. So that would be 0.05 times 0.02. So this, I think it's 0.0. Let's check. You can use your calculator. 0.05 times 0.02 is 0.001. Another example. Suppose that P of A given B is 0.4. A given B 0.4. P of B is 0.5. What is the probability of A intersection B? So the probability for A intersection B is equal to P of A times P of B times P of A given B. So that's 0.4 times 0.5 equal to 0.2. How about the probability of A prime intersection B? So how do we solve for the probability of A prime intersection B? So what we can do here is to check. This is B, this is B prime, so that is 0.5 each. So the probability of A given B is 0.4. So therefore, the probability of A prime given B is the complement of 0.4. So that's 0.6. So the probability of A prime intersection B is equal to the probability of A prime given B times P of B. So that would be 0.6 times 0.4. So that would be 0. Sorry, that should be 0.6 times 0.5. So that's 0.3. Suppose that the probability of A given B is 0.2. So the probability of A given B is 0.2. The probability of A given B prime is 0.3. And P of B is equal to 0.8. What is P of A? So what we have is B 0.8. So B prime is 0.2. The probability of B given A given B is 0.2, and the probability of A given B prime is 0.3. So to solve this, we add 0.8 times 0.2 plus 0.2 times 0.3. So 0.8 times 0.2 is 0.16, while 0.2 times 0.3 is 0.06. So we have 0.22. Next example, so suppose that P of A is 0.6 and P of B is 0.3. And the probability for the intersection A intersection B is 0.15. Determine the probability of A given B. So what is the probability of A given B? So that would be P of A given B is P of A intersection B over P of B. So A intersection B is 0.15 over 0.3. So that's 1/2. Are the events A and B independent? So they are independent if the probability of A given B is equal to the probability of A. Is 1/2 equal to 0.6? So no. So this is not independent. Next. A manufacturer of computer keyboards has assembly parts at 2 different locations. One in Iowa. This is for Iowa. And the other in South Carolina. The keyboard's faults in general are classified into 3 different categories: letter, number, and others. So the summary of the last year's inspection of production is estimated the fault rates as follows. If the keyboard from the manufacturer is chosen at random, the event's faulty key and produced in South Carolina facility of each other. So if a keyboard from the manufacturer is chosen at random, are the events faulty letter. So faulty letter is being a faulty letter key and produced in South Carolina, independent of each other. So just to simplify, we can have P of A times P of B must be equal to the probability of A intersection B. So let's have the total. What is 15 plus 45 plus 40? That's 100. So 75 plus 30 plus 45, that's 150. So all in all, we have a total of 250. We also have the total of 15 plus 75. So this is a total of 90. P of A, we can have that as P of A is 90 over 250. And P of B is 150 over 250. And their intersection is 75 over 250. So let's check if they are the same. 90 times 150 over 250 squared is 27 over 125. Is it the same as 75 over 250? This is 3 over 10. So they are not the same. So this is not independent. For the reliability of events, if we have a series of events given by P of C1, P of C2, P of C3, P of C4, what we do is we multiply their probabilities. While if we have parallel events or parallel configuration, the total reliability for this one would be 1 minus P of C1 times 1 minus P of C2 and so on. So the reliability of series is the product of the reliabilities of each component, while for the parallel, it would be 1 minus the complement of each reliabilities. So 1 minus the complement of each reliabilities. So let's have this one. The following circuit operates only if there is a path of functional devices from left to right. So left to right. The probability reliability of each of the device is as shown on the graph. Assume that the device fail independently. What is the probability that the circuit operates from left? Let L and R denotes the event that the left and the right devices operate respectively. So the probability or the reliability is 0.8 since they are connected in series times 0.9 equal to 0.72. Another one. The following circuit operates if there is a path of functional devices from left to right. The probability reliability that each device functions is shown in the graph. Let T and B denote that the top and the bottom device operate respectively. So the reliability is 1 minus 0.95 times 1 minus 0.95. So this is 1 minus 0.05 squared. So this is 1 minus 0.05 squared equal to 0.9975. So observe that if you have two events that are not so reliable, or if you have two reliable events, the series operation between these two events would be lower than the reliability of any of the two. So the total reliability 0.72 is lower than 0.8 and lower than 0.9. So you don't want to connect them in series. But if you want to be more reliable, you connect them in parallel because the result would be higher than the individual reliabilities. Consider this one. So this would be R1 times R2. So that would be the reliability, R1 times R2, because they are connected in series. And then it is connected in parallel to this one. So the result would now be 1 minus R1, R2, and then 1 minus R3 of T. So this is the reliability. For this one, we take the total reliability of the first branch and then the second branch. So it would be 0.9 times 0.8 times 0.7. So that's 0.504. Observe that it is lower than the individual reliabilities. Next, your reliabilities of 3.95s would be 0.857375. So 0.857375. So the total reliability is 1 minus 0.504, 1 minus 0.857375. And then you can evaluate that. So then the last one is set for you as an exercise. This summarizes the topic about probability. You can pause this while the references used are this one. So have a good day.